and a few of them are quite successful now. So the group was really born out of that. It was born out of giving them a showcase to talk about some of the things that achieved through this startup journey. And we didn't actually do anything for about 2 years because rubbish. So what I decided to do was to hand the reins over to Sandy and Tim, who've got some really amazing grand plans. So I'm going to let them describe what the next 6 months looks like. Yep. So here you go.
Hey, so I'm Sandy, and this is Tim. So as Richard said, we've taken over the reins of IoT and data science innovators with some help from Carlos from Data Science London and Laura from Inspiring Women in Data Science to put this event on today and hopefully have some of you guys come back. So Andrew is going to do our first talk, and we're kind of just looking to bring amazing content to people. So what me and Tim get to do, we get to speak with lots of interesting people. I met Andrew at Spark Summit in Dublin last year, and we get to see some great talks, hear some great content, and we want to try and meet people and bring this back to the London IoT and data science community. We've got some ideas about bringing workshops to you guys, setting a lab up possibly in a space like this on a Saturday, things like this, and seeing what we can kind of do and achieve together and what we can bring to the community and come together and give everything back. So, unless you, anything?
No, nothing.
No? So, please sit back, enjoy the great talk from Andrew.
Oh, you have a mic. I have a mic.
You have a mic.
So, my name is Andrew Morgan. Has anyone seen me speak before? I've spoken at a few events in London, and I spoke in Dublin, so a couple of the guys. That's great, no one's seen me before. So I wanted to open up today, and the guys asked me to speak. So Richard said to me, you know, what can we talk about that's really cool, that would interest the IoT kind of community, and be relevant to data science, and we need to open up this thing again with something that kind of is going to spark interest, right? So I'm going to talk today about some experiments that I've been playing with on the side. So I was thinking about some really important things I could do. And then I thought, no, everyone wants to know what fun I'm having, because I'm having a lot of fun. And so why don't we come and talk about some of the fun things that we're doing? So I'm going to start with like an introduction. And I'm going to introduce kind of where we are now in data science. Because like when I started speaking at these meetups in 2013, we're in like a really different place today than we were then. And back then, everyone thought big data was cool, and I thought it was cool, and now no one wants to talk about that anymore. And so there's a number of changes that we need to just address. Then I'm going to talk about some real problems that are out in the wild and also that I'm having. And then we're going to talk about some cool software, because I think you guys came for that. And then I ran an experiment to see if it works, and then we're going to have a look at the results. And then we're going to talk about a little bit about the outlook, although I think I ran out of steam on my slides, so that might be short. So I want to just lead with where we are now. Oh, God, that's really annoying, isn't it? OK. There's two kinds of people, the kind that can't infer from missing. All right, hold on a sec. Let's see if I can't fix it by making it smaller on my screen. Because that might work, actually. Will that work? No, that'll just be worse, won't it? Oh, God, that's even worse. OK, so yeah, I think I will do that. OK, so basically, I'm going to swap to my reading glasses because I'm reading for you now. It's like a bedtime story. There's like this AI revolution that's happening today that in 2013, it was just starting, and it was a little bit on the outside, and no one really knew it was going to land. Everyone was kind of thinking a little bit about deep learning, but no one had really done it. There was a number of people who were really cool talking about it. And I went out and learned like Lua. So I program in Lua badly. It's one of my large repertoire of bad languages I program in. And I got into Torch 7. I started playing with neural networks. And there was this whole thing. It felt very exciting. And there was this revolution. And so the question is, like, why would we look further today? Because now it's kind of really landing. And in that time, what happened was all of the customers I spoke to started talking to me about AI. And at first I was like, AI? And I'm like, some guy's talking to me like my my AI, and it was all about my AI and your AI, and we're going to deploy this AI. And I was kind of still scratching my head thinking, no, I'm like an engineer. I'm building large-scale models. I'm deploying models, right? And this AI agenda, no matter what I did, it just kept coming back at me. And so it changed the scope of what I do. And so we have some of the people on my team who are, like Deanna's here today. And it actually just changed my job. So, and I never made any claims about AI. So I didn't create a robot called Data. I don't know anything about Terminator. I'm not into dystopias. But what happened with this kind of agenda was things were working on big data, so I learned Spark, and I'm a big data guy. And then the jobs for big data stopped coming in, and people weren't getting me to do big data jobs anymore. They were getting me to do medium data jobs on sort of other types of data. And I ended up doing a lot of deep learning, a lot of data science, and then slowly I'm getting pushed into working with customers that are in this data poor environment. And in data poor environments, people are looking at optimization, there's scheduling problems, like some good old-fashioned AI problems in this space. And I kept saying to people, no, we're like the machine learning team. And people were saying, no, you're like the AI team, right? And okay. So how does that change what we do, and what does it mean for us? And is it time now to start looking at sort of, I call it good old-fashioned AI, like there. Some of the methods that were really cool before are coming back into favor, and now actually a lot of people are having to like widen in breadth. So this is all the backdrop to something else that's going on. Recently, there's been a number of people who are asking questions, okay? And these are kind of questions that we wouldn't have asked 2 years ago because we were all so wowed by deep learning. People are now saying things like, hey, I've got some critical appraisals of deep learning, right? Is this really the AI technology that we're all hearing about? So this AI agenda now is questioning our progress in areas like deep learning. And so this great paper came out. It's worth reading if you haven't seen it. It's called Deep Learning, a Critical Appraisal by Gary Marcus. And I've got the links down on here, so this will be available afterwards. But basically, in a nutshell, he basically says that AI is a tough problem, that deep learning is just a part of the problem or a part of the solution, that maybe there's ensemble methods that help work on wider scale real AI. And he kind of just raises these concerns. And when he raised those concerns, around the same time this came out, Geoffrey Hinton, who kind of was one of the fathers of deep learning, and he came out and expressed a concern, which it got all over Medium, which is like a website. And he then said that he's kind of uneasy about backpropagation. Well, this is like what deep learning is all about, right? So we're all backpropping, and we're spending all this money on GPUs to do this. And he's kind of just said we should throw it all away and start again. And it left a number of people kind of cold, like, what are we going to do? And so there's this feeling that there's questions, there's a feeling that things are changing, and there's a feeling that if there isn't something new around the corner, that maybe there should be, okay? So what that means is that, people like me, I'm really super curious. I start like putting my feelers out and start thinking like, well, if this isn't it, what's the next big thing? So it got me very curious. And it got me curious enough to read the paper that they linked to in that article. And in this paper, it's called Neural Optimizer Search with Reinforcement Learning. In this paper, these guys here have proposed a mechanism for replacing backpropagation. And they're thinking about replacing backpropagation in these trials using a genetic algorithm that sets out an equation to do the updates, okay? So it's really technical. I read it 3 times. I'm still not sure I'm good at explaining it, so I'm not going to do that. But there is a link, and I really recommend for the people that are really technical, go and have a look at this. But it's very cool. And basically, in a nutshell, they're going to use backpropagation on a toy network, and they're going to take the update weights that they get, and they're going to train a machine to create an equation that propagates the same weights with a minimum error. Very interesting idea. So in this paper, what I picked up was this little line that I've highlighted that says the key difference is that our approach generates a mathematical equation for the update instead of numerical updates. So now I'm thinking, okay, what the heck does that mean? You're generating equations? Okay, so I don't have a computer science genetic algorithm background, so I'm just thinking this sounds like magic. So I got curious, of course. So getting curious more and more about all of these conversations, and they all seem to be leading to something like genetic programming. And this idea about genetic programming is the output of this model is a is an equation. It's a symbolic equation. So I thought, well, maybe this is time for me to broaden my horizons and start looking into this. So I went and read this book, and I bought it. So it's a really big book, and it's really expensive. So I suggest you go to the library and get this book, because my wife saw the price, and she's like, what? You spent like 130 quid on a book? So she was just shocked. But it's an excellent book. And this book is something, it's about gene expression programming. Does anyone know what that means? Has anyone tried it? So there's a couple people who've heard of it. It means that no one else knows what I'm talking about, so I should probably explain that. In a nutshell, gene expression programming says that we're going to express an abstract syntax tree, right, that represents some code, and we're going to have two things. We're going to serialize it to a string, and we're going to call that genes, and then we'll cast it back into an abstract syntax tree, and then further we'll then use a template of some kind to generate executable, compilable code, right? So there's three different pieces. There's the string expression, the string representation, then there's the expression of that code into functional units, and then there's the compile stage where you make a functional running component that you can deploy. So this book then explains that you can have multiple genes creating multiple steps. You can create hierarchies and nestings, and very interesting ideas in this book. So I recommend, of all the stuff I read, this is the best bit I looked at. So I started looking around and thinking, okay, so here's one of the answers that sounds cool. What are the problems? You know, typical IT guy. So let's have a think about what we need. So I wanted to say, and you can't read that there, of course, that there is a challenging life cycle in data science. And a lot of non-practitioners outside of the data science arena, so people asking for AI, they don't appreciate this challenging life cycle. And so I'm going to just tell you about what the problems I'm facing are. So this, just to explain what it is, there's three kind of competency centers, and they sit and they are collaborating in this area here. So in this case, this is an old diagram. We had enterprise data architecture, data science, and when they collaborate, we're going to inform hypotheses. And the idea being that they interface to the business and users. And when these guys work with engineers, they innovate and create innovative engineering projects. And when they try to go into production, then there's these industrialized integrated flows. And so this is the basic wheel of life in data science as we go from idea and ideation over to prototypes and then into production. So are there problems there? Well, yeah, so there's quite a few problems. First of all, there's a lot of tough cultural challenges around getting great hypotheses. And actually, the AI agenda has made it even harder, right, to generate great hypotheses. In this diagram, you see I actually call it out. I say, you know, what I do is data exploitation. And now with AI, people say, no, we don't need data, we need AI, right? So we're having this challenge around training data. We're having this kind of confused conversation that's moved away from these core principles. In the prototyping stage as well, people are saying, wow, but they're not necessarily signing the check I need to go to production. And that's really annoying. So I'm like asking people why. So example, I'm one of the first people in the UK to automate claims insurance. So for a critical illness, there's a process. If you get cancer, you put in your claim. About 6 weeks later, you get a determination whether they pay. So I got this process down to 15 minutes, right? That's a pretty big step change for the business. And it just used random forests and stuff. It was just simple, but it turned out they asked all the wrong questions. And we figured that out, and we changed the process. But they never went to production. So the question is, why, with such a great use case, would you not go to production? And it's because the production costs are too high when we move around to the bottom left, to the industrialization stage. And they say stuff to me like, well, we have this legacy mainframe, this RS-6000, and now you've asked us to have industrial changes to our flows. So now we're going to open up networks, we're going to stand up services, we're going to have a model serving component with an API, but we're not sure how to do that from a mainframe. And you know, then there's this old crabby engineer who's just like not interested. He's just coasting for his, you know, retirement. So it's a very difficult conversation, and there's a lot of cloud aversion at this place we're at. So there's a lot of things that are hampering real companies from making these changes. And then the last thing that's really kind of there is around this data poverty. Data poverty is no longer an excuse for me not to have a go, right? That's what people are telling me. And so now I'm looking at alternative techniques that are useful in areas where there's not enough data. And so deep learning, for example, it really suffers where there's no data, right? So there's a whole challenging life cycle there. Does that resonate with anyone in the room, by the way, all these problems? Is that just me ranting, or is that? I'm seeing some nodding. Okay, so that's a good sign. The other issue that's going on, and I'm going to call this out because this is also for, I really hate that. Retrofitting AI is really not easy. Okay, so what I mean by that is somebody will arrive and say, I've got a running system. It's been running for about 9 years. It's quite kind of today, it feels a bit legacy-like. There's an old-fashioned database, and it's in a 3-tier architecture with an app layer, and there's like some kind of UI. And what we want to do is we want to have some AI in our UI, right? That's the words. So that's a scary set of words for me. I'm like, oh, AI in the UI, right? It sounds like a chatbot in disguise. So I'm finding, though, that these models now are having to get into, and that should say getting models retrofitted into running systems is really hard. And it is hard. And what's hard is that you land in a place that looks like this, and your giant ML model that you've created is going to fit somehow into that box. And it's just really, it's a difficult sell to all of the people who operate these complex machines, right? And then the other thing that's happening in more IoT spaces is people are saying, hey, can your great big gigantic Tensorflow, tensor serving model thing, can it go in my watch? I've got this computer, it's about the size of a Tic Tac. I was wondering if it can run like model serve kind of, APIs and stuff. And I'm like, well, yeah, I'm not sure about that actually. We might have to do it over the internet, and then like connectivity, and you can see the mind turning as this doesn't really compute for people. So there's a number of questions that people are putting to me, and some of them are kind of amusing to me. And they are stuff like, can't we do the AI without introducing an API? Right? That's a simple request, And I asked, well, why is that? And they say things like, well, if we had a smart city and we lose the internet, then all the traffic lights will stop working. Right? That's a terrible idea, right? We want them to be smart even when we're not online. And then I asked them, tell me more. And they say things like, well, I don't want my phone to lose connection and get dumb. I'm tired of Siri not being available when I want Siri available. I want that model in the device. I'm like, okay. And then on the industrial side, I'm getting people saying things like, put that AI in a legacy mainframe, which is just going to be hard. At least I don't know how to do it. People are saying things like, can you deploy this AI thing? Can you put it in a stored procedure in MySQL or in stored in SQL Server and other types of databases? So I know SQL Server really well, and I've never deployed a machine learning model in a stored proc. And I'm thinking, well, all right, that sounds like a terrible idea. I'm sure there's ways to do it, right? Can we run the model on like an Arduino, right? This is another idea, right? I actually didn't hear that. No one's asked me that because no one in business knows what that is. But that's the kind of thing I'm getting when I look at these little watches and little things. And all the time, I'm saying no, and I'm kind of rolling my eyes. But I'm really wishing I should say yes, right? I'm sick of rolling my eyes and saying no. I want some happy customers who ask for crazy, and I can do it, right? That sounds like a great idea. So I want to say yes. So these IoT-specific challenges, then, I'm going to make a list of them. So big data science, still not easy, okay? It's the theme of the book I wrote recently. Model portability is one of the key challenges that we need to face up to, okay? And this is getting better. I'd say out of 10, it's still not great, maybe 6. Legacy systems, now that legacy companies are getting involved, and old companies and enterprise-y type customers are getting involved, this is hard. There's constrained edge hardware. And in edge devices like my Fakebit, it's hard to get these complex models in there, right? There's also this problem with intermittent networks. So we can't just keep telling people we're going to step away and have an API. People are getting wise to the costs, and they're saying no. In another life and another question, this idea of model distribution is coming about. So, and it comes along with a further discussion around model jurisdiction. Does anyone know what model jurisdiction is? Has anyone heard of this? So the simple way to explain it is you're driving your automatic car that's driving itself, and it gets on the ferry and it goes to France, and it drives on the wrong side of the road. So actually, the machine learning to drive a car is jurisdiction bound, right? So as you pass from France to Germany, the road rules change. As you go through to the UK over a ferry, it changes. So now we have this geofencing requirement for models. And to do that, we need to have a model distribution engine so that if some device finds itself in the wrong jurisdiction for whatever reason, it can call home and get the local model. Right? So this is an interesting IoT idea, and we need to start thinking about model distribution. But when your great big RNN coming out of Tensorflow, and you've got some LSTM model, and it's like 200 megabytes, it sounds pretty small until you have to distribute it to 1 trillion little devices, and now you just DOS attack the whole world, right? So it's actually, it's a question. So how can genetic programming help us? And why might this be helpful? So genetic programming, its output is not some big complex set of matrices. Its output is an equation. And I'm going to walk you through this later, right? It outputs equations that do regression, and it outputs equations that can drive classifications with a few if statements about greater than or less than. And in this area, we can now evolve an equation using a fitness function over training data. And this output, it's small. You can write it on your arm. It's that small. So that sounds about the right size to distribute to millions and trillions of little devices. It sounds like it's really easy to then code that up as a UDF in SQL Server. It sounds really simple to deploy that function as a C package as a little tiny compile thing that goes in this embedded device using some kind of deployment mechanism. So that's my hypothesis. And I think it could really simplify glide paths to production that I'm finding tricky. Now, the question just is, will the models work? So if I tell you I have a great model, but if I degrade its performance by 30%, we can get to production, then the question is that going to fly, right? Is that real? No one's going to like that. The other thing is, can I get it running? There's loads of cool people online, and they're doing all this cool stuff. Half the time, I can't get it running. So I'm always a bit of a stickler on, like, if I can't do it, really nobody can do it. On results, we need some kind of estimation on whether we could get good results. And the last question is, will it scale? And this is one of the big criticisms I read online about GP in general, is that it could be slow. It might not work for big data. So those are all the things I wanted to look at. So when I talk about genetic programming, I want to just show you this picture. So this is an equation, okay? A times A minus 5 divided by 3 times the cos C. And this is how a genetic algorithm views that equation. So if you're old like me and you might have used a reverse Polish notation calculator when you were young, okay, you'll know that there's different ways to draw up equations. You can put 2 numbers and an operator last, or you can prefix and say operator, and then the parity of the equation dictates the terminals, right, that you put in. And in this mechanism, if you trace the root, which is a slash, well, actually that's the divide at the top. So the root of this equation here, the division, is in the center, and then the division has a left and right terminal. So the left one here, instead of a number, it's been swapped out for another function that has 2 parameters, 1 to 5. The other one has been swapped out for a star and an A and an A. So what you're doing is you're building this nested structure. So we're representing an equation through these abstract syntax trees. So this is the magic of genetic programming, is that first the representation here can be manipulated. And so I have been talking to a guy whose name is Kai, and he wrote some amazing software, which I'm going to show you, that runs genetic programming and training of genetic programs on TensorFlow. And he has this great chalkboard. So he actually sent me a picture of his chalkboard from when he was doing his PhD. And he's like, oh, yeah, it's really simple. So it's like digital brown paper. It's amazing. So he's got the chalkboard out, and he's worked it all out. But basically, there are different kinds of functions we can put in. So an if statement has 3 terminals, right? A multiplication 2, a not just has a 1. So you can see that there's an arity. And in the notes that you can see is sketching up, he's doing math on arities, right? To find out which parts of an abstract syntax tree can be swapped out with which other parts, so that it doesn't break the executability of these abstract syntax trees as they mutate. Does that make any sense so far? Have I lost anybody? Some of the business people. You still with me? Okay, good. All right. There's a question about, so if you were going to tune up a random forest, you'd say, well, how many trees would I have, right? So in genetic programming, we also are being introduced to this idea of model depth. And that's the depth of these models, right? The amount of nesting and operators that we can have. And if you multiply the depth by all the most complicated arities, you can kind of work out the space of the model. So this is a search space. And we have all these terminals, we have all these functions, and we're going to build this kind of grid. And we're going to start to do things like we're going to build an initial random population, and then we're going to start testing if this function that we built is good and fit for purpose, and that will score up with some kind of a fitness score. And what we'll do is maybe we'll have a parent, and we'll have some randomly generated branch, and we'll start to swap in for one of the random parts of this abstract syntax tree, the randomly generated component as a way to mutate that code. So what we're going to do is we're going to find spots on here that are sweet spots. We're going to swap in this code here to create some offspring, which is a new function. And this is the basic idea behind genetic programming, is that these abstract syntax trees can be edited, mutated, and you can do reproduction and fold parts of code into other parts of it. But actually, if I said to you a to the power of b, that's a lot different than b to the power of a, right? So small changes to these equations can have massive differences in what the equation's output's going to give you. And so these small edits, while looking very innocuous, actually have a massive difference to the performance of these equations, okay? Actually, I've somehow come out of my program. So I'm going to show you reproduction. So there's a number of operators in this kind of space for genetic programming. And so parent A and parent B. In this case, there's a different size depth, and there's different things going on. And so there's a random selection of that terminal. And again, we have picked off this one, but it could have easily been another one. And what we're going to do is we're going to generate 2 children. This one is swapped over there, and that one is swapped over here. So now we have 2 children that share most of the genes, in quote, of their parents, but they're going to be different, right? And we all make jokes about our friends, how beautiful their kids are, and how did that happen, right? And so this is the genetic approach to evolving a population. Now, we've all heard of Charles Darwin and the idea of natural selection. So what if we only did this process on things that had high fitness? So if we had 100 people and they all threw a dart at a wall, and we only allowed the reproduction to take place for people that hit the board, right? Then what's going to happen is that the equations that we're actually evolving are going to be always targeted on best fitness. And this constant search and repeat is driving our equations towards the answer. So that's the whole idea of this genetic programming. Still everyone with me? All right. So let's have an experiment. This all sounds like great in theory, but I like stuff in practice, right? So let's have a hypothesis. Now, a lot of people heard me say this, but I have a syntax for hypotheses. And like in Agile, you have like as a user. So I have a syntax for success, as my friend calls it. So using a benchmark data set, that one, we can use a genetic programming tool to train a regression model. And it's going to be competitive with other ML models so that it's worthwhile doing. And it's still going to be highly deployable at the end to these constrained environments, right? This is this kind of watch idea. And we're going to do this, and we're going to be able to deploy these equations with minimal additional junk that goes with them. So there's not going to be like a pip, pip install loads of stuff to run this model. We're going to generate an equation. It's going to go straight into some SQL statement. Does anyone think I can do this? Yeah. Come on, yeah. You believe in me? I don't know. I wasn't so sure. I actually signed up for this talk before I finished the experiment. I was getting really nervous. So the idea is that this is a fun thing to play with. It might not work. I'm not going to tell you to the end. So this data set, we have to, first of all, have some ideas of our hypothesis, okay? So I, first of all, went and found some software. And you guys all got to check this guy out. It's called Karoo, GP, as in genetic programming. Oh, it has a great website that we can't see. And Karoo GP is genetic programming library in Python. So it's on GitHub. It has its own page. You hit Google. If you type in Karoo _GP, there's only one of those on the net. It'll pop straight up. I recommend you start on GitHub. It comes with this really nice little interface and makes it super easy to use, which I was loving. It's scriptable, so you can set up a cron job and run loads of these, and you can move it around. And what was the amazing piece about this software that I loved is it employs Tensorflow to do the fitness functions. So I'll explain what that means, but that got me hooked right away. Just like you guys all came, I was right in. And it also, as an output, it can generate the raw abstract syntax trees, as well as it lays them out like an equation, and it also rationalizes them into Python equations using the SymPy libraries. So that's very nice. And it's open source, and it turns out this software is battle tested. And so when I talked to Kai about it, I said, like, what does that mean? So he actually developed this software with a bunch of, he developed it as part of a use case for the 1 kilometer grid array in South Africa, which is like a giant telescope. And there's a head of ML over there, and he was working with these guys. And they wanted to try using genetic programming to solve a bunch of problems that they had. And again, if you think back to IoT, this is a huge array of things, and genetic programming is probably one of the answers for them. So it's kind of been in flight, and it's through various types of edit. I've been raising some tickets to improve the software from when I played with it. So he's very keen, and he's been super helpful. So our experimental design. So if you guys don't know H2O, it's a machine learning library. It has a really nice UI, and it's like data science for the lazy. It's great. You just load up your data, you hit go, does a whole bunch of science, and tunes it all up for you. And because that's not our experiment, I just want a baseline. I'm just going to open it up, hit go, let it run, get some scores, and then see if I can't get my genetic algorithm to generate something in the ballpark, right? So we're going to do that, and then we're going to run the regression model in Karoo, and we're going to see the genetic operators in flight as they edit. We'll do that. And then we're going to compare the model performance, and then we're going to see if we can't deploy the code that comes out to something that I would consider constrained. So I'm going to, because I'm a Spark guy, I'm going to put it into Spark SQL. So I just want to pick it up, copy it, and hit paste, right? So that's if I could do it there, I could do it in MySQL, I could do it in SQLite, I could do it in Postgres, I could do it in anything. So for me, that hits a lot of the challenging problems I had. And then I think there's some discussion around tuning, because these things are not as intuitive as I thought. So let's walk through some of the user guides. So it turns out that this software has a great 10-page PDF. And I'm literally going to just show it to you, because it's way easier than me just copying and pasting it. So this is the website, Karoo GP. And it has a nice little description. And that sounded like a bottle of champagne. That's for after the talk. After the talk. OK, so he walks through some use cases about how the software works. And I could never do a better job than just flicking through this. We're just going to flick through this quickly together so that we all understand what's happening. OK, so we have parents, A and B, and then they have children, A and B. And they replace parents, and we're going to evolve. So in here, there's a lovely table of contents about what you see. I'm going to skip over some of the stuff. Oh, in terms of installing the software, that was probably one of the hardest things I did. You need to install Tensorflow, so you need a machine with a GPU. Oh, it's being cut off again. So Python, NumPy, SymPy, TensorFlow, scikit-learn, and Matplotlib. So not too difficult, but you need to find a machine with TensorFlow. Or you can run it with TensorFlow CPU, and that works just fine too. It turns out that actually the vectorization of the operations is what the big speed up was around. And so actually Kai says to me that it runs almost as fast in CPU, about 10% faster on GPU. If we go down, you can install it on a Mac. If we go down, there's a whole bunch of guff here, but we see about the base tree depth. So these are the settings that I'm going to use with you guys to show you this worked example. Oops, there we go. So we're going to set our tree depth, and that's basically the complexity of the most complex equation we could set. So if you guys worry about overfitting, if this was humongous, we could overfit. So we're going to try to trim that and keep it small for this demo. The maximum tree depth, the minimum number of nodes, the number of trees in the population, all key settings. So I'm going to use defaults with this because it's easy just to run with defaults. But say we had a population of 100 individuals. So that's these trees. And then what we'll do is we'll have to set the number of generations over which they evolve. So we'll just use like 10 to see if we're getting the ballpark. And then there's a nice interactive screen. And what it's going to generate for us when we see it is the leading trees are the ones that were the most fit, that fitted our data the best. So these are the ones where the regression has the minimum mean squared error. So out of the 100, we'll pick off the top 5 or whatever, and we'll see what they look like. And the operators we're going to play with are reproduction. God, that's really annoying. We're going to look at reproduction, point mutation, and branch mutation. Right? So these are the key areas. So I think we touched a little bit on these. A point mutation is just literally you swap something out. Very handy to test lots of coefficients, for example. And then something called crossover, where you grab parts of trees and you swap them over. Now, the key thing with all of this that made TensorFlow in the game or out of the game, when we think about this structure, everything that's not a terminal, like a number, is a function. And we can give this software the list of functions it should use. Right, that's cool. So we could just give it the big 4, right? Plus, minus, multiplication, and division. Or we can give it tan, cos, sine, atan. We could start to put in, I don't know, other functions. But how about we did something cool? We just limited those functions to ones that have something that executes in the TensorFlow API. If it's not in the TensorFlow API, it's not in my list. It means that everything I generate is TensorFlow ready, right? So that's a very interesting constraint. It doesn't have to be that way in the software, but it is this way. And because of that, it means that when we go to build this equation, it is TensorFlow ready. I can just get my TF reader, throw all the data in, and I can literally rip down the 100,000 test cases, generating the answer, and then I can calculate my MSE off how well it did against the actual. Right? So that's the big trick in the software. If I just slide down, for example, there's a list here, and you can see that there's operators file, a CSV file, and you literally just stick them in like that. So if you wanted to go and use specialist ones, you probably could set it up, and you can change the software. It's all open source. I mean, as I've been playing with it, the simple ones win. I just wanted to point out something interesting that's going on here. You know, I talked about the big 4, but it's down here 4 times. There's lots of pluses and minuses going on. And so what's happening in the software, it's randomly picking from this list. So if you want to game the system by having more pluses and minuses, you stick more of these operators in the list. And so the probability of any one coming up is now swinging towards the arithmetic operators, right? And less towards the tan and cosine. So this is a really different way of thinking about setting up your experiment, right? So there's an idea with the data. Something else that's really funny about the software that I haven't really quite got my head around, but when you're generating these functions, there's this idea that you want to have a whole bunch of numbers as variables, and then you might want to adjust them by coefficient, like a weight. And to generate those randomly, actually, the way the software works is you feed in the numbers you'd like as hard-coded numbers to go in as null columns, just zeroed out. And he'll pick them off the headers. So it's a funny way to prepare your data, but that's how currently it's the quick hack he did to make it all work. And actually, it's been working fine for me, but it's just a note. And the other thing about this is that it's just a simple CSV file with headers, and the answer is always called S. I don't know what that means, but it's always S. And we go through some of the details, and each one of those trees can be output from the software, and it'll be having a tree ID, and it'll have a bunch of details about how it's actually loaded up. And those can be used to serialize and deserialize your ASTs. So you can flush them all to disk and save your work, and then you can recall them later. You can then start to run things yourself. So you could kind of game the system and do things. So that's a pretty good opener. I'm going to now, this is where it's all going to go wrong, right? Oops. So I'm going to kill that. I'm in a screen. OK, will this work? OK, we're running the software, and it's adjusted. I'm going to move my screen just a little bit so it doesn't get cut off by that annoying piece at the top. I'm going to just realign this. OK, so when you run the software, I'm actually going to just kill that and show you the command line. So literally, you can kick it off on the command line. I downloaded this software, git clone, Python, the main library in Python, the directory of my power plant data, and that's basically going to initialize the whole thing to get all your readers. You don't have to do any funny business with TF reader or anything. It's just going to load it in, and away it goes. So we hit go on that. It's going to bring up a UI, a terminal-based UI, and it says, like, Karoo GP, like hello world, and it asks you what you want to do. So it's going to say classification, regression, matching, or play. I'm going to go for a regression because that's our task. And it's going to ask me some of those questions. So it's going to say, would you like a full grow or ramped method to adjust those trees over time? So a full one means if I set a depth of 6, and I would always generate 6 deep and so wide, and I'd have a whole grid filled in with numbers. Ramped means it's going to do a few of each, and it's going to slowly adjust it up over time. And grow means we're going to start small and slowly, incrementally get bigger over time. Okay? So we're going to go for the default ramped. We're going to enter the depth of the initial population. So the initial depth, meaning how complex that equation can be, we'll say the initial depth will be 4. We're going to go for it, right? And we're going to say that the maximum tree depth is 7. So that's quite a complex equation. And then the minimum number of nodes for any given tree, we'll put it in as 5, because we think that this is a fairly complex data set. And I'm just going to show you that before we hit run. And we're going to enter the number of trees in each population. Use 100, right? Maximum number of generations, we'll put in 10. And we'll let this spin while we do some more talking. And I'm going to make it interactive so we can just see what it's doing. So it says we've constructed a population of 100 trees for generation 1. Evaluate the first generation of trees. And now it starts generating. And you can see slowly, it tells you the tree that it created. So it created this random function. It ran a regression against the output. And it told me the fitness of that. All right? So that's it. And we're going to try to, and it's done it 100 times. And did everyone catch that? Should I run it again? We're going to see it again anyway, because we're going to run next generation. So it's now added all of the nodes to the gene pool, and it's gone in. It now is performing 10 reproductions. So the 10 best ones are going to get reproduced, right? And not the rest. And now it's going to go through a tournament. And the tournament is where it grabs stuff and chooses. So tree 67 is a fitness of X, and it leads and is ignored. So you're going through and you're grabbing a tournament, and then you have to just choose a winner of the tournament. So it's going through like a moving window of potential reproductions, right? And it's choosing winners. And it's doing it on fitness. If we go through again, it's now doing these grow mutations, and it's growing those again. It's doing crossovers. And now it's going to go through evaluation 2. And if we just have a look at what it says there. So it did some tournaments, and it shows stuff from mutation, and it did terminal crossovers from parent 96 to offspring 62. So you could track and trace every single equation and its heritage. So we could have a family tree of equations. That's kind of crazy, right? So we could actually, if we had some kind of fancy visualization tool, we could watch the mutations happening and see how the children are getting better. It would be really kind of cool. So we go through, and we're going to do this again, and it's now doing its gene pool, and we're going to go through another 10 reproductions. So I'm going to kill that, because that could take quite a while. And I'm going to, come on, quit. Maybe I'm going to have to just let that go. That's what's great about Screen. I can quit it like that. So we're going to do that again. Bash profile. History grep. Okay, we're just going to run it again, and this time we're going to run it fast because we want to see the, oops, where am I? I'm in the wrong directory. Gap. Sorry, you're going to have to suffer through my terrible typing. Okay, so this time, instead of running it in the slow interactive mode, did you guys like the slow interactive mode, by the way? That's so cool. So when he did this, he was using it as a demonstrator to teach his students. I think that's what it was, but I found it extremely useful when I got playing with this. So this is why I'm recommending the software, because if you're going to get into this, it's not easy unless you've done a degree, but this makes it much easier. Again, we're going to hit regression. We're going to go ramped. We're going to just, I'm just going to grab all the defaults, and it's going to default to minimum. So it's just going to buzz away there. Now, what you have to realize, every time you see one of these equations rolling up the screen, it's done 10,000 runs of that equation evaluation. All right? So it's moving fast on my GPU. So I've got a GTX 980 Ti in my old box, and it's basically, we're going to open it up and see, because this is what experiments are about. I'm going to go in here, and we're going to watch that. Okay, will it let me in? It will. It's just being slow. We're going to open up my NVIDIA. We're going to see. So let's have a look at my GPU. Let's see if we're really killing the machine. It turns out we're not. Like, I got a 0 volatility. I've got a load of stuff running. So I'm running Karoo in parallel in loads of screens. So I'm actually running loads of them at the same time. And you can see that my GPU fan is on like 0, but I think that's because my window's open at home, it's cold. But it's really not even breaking a sweat. Like, I'm using 16 watts of 250. For me, when I run other things, like I ran some Bitcoin mining, this thing was heating up my office to like 30 degrees. Like, seriously, it's in the garden. I didn't need a heater. It was cold. So this thing is not even breaking a sweat on my GPU. So we could probably run lots of this in parallel. Let's just go back where it's running. So the one I'm running with you guys is the one at the end. No. Okay. Is that the one that we had? Okay, let's just go back up a bit because I've lost the bottom of my screen. Okay, so I'm going to show you, I think this is actually the wrong screen, but this is the one I had before. We're going to list. So it created a leading set of associated trees and the answer. So it looks like for that equation, that could be the answer. So just before we look at the output of this, we're going to flip over to the internet, and we're going to have a quick look at a cool website. So this is a guy who has the UCI power plant data. So it's stored on my GitHub. If you want it, you can go and grab the data. And it turns out that someone helpfully over at Databricks has been playing with this data set. And they have been doing some work drawing and playing with it. And in fact, I think it's here. I think that's it there. So it's this woman here who's done the work. We're just going to go flick through and see if we can't power. Here we go, power plant pipeline learning application. So she's got a nice Python notebook, and we'll have a look and see. Oops, oh bugger. You know what? I'm not going to be able to do that. Okay. Is it still open? Okay, so she's basically gone through and shown us her results. So, sorry? Okay, so it's about 9,700 data points, and what it represents, so I actually can't open that up now without killing my connection to my machine, which I don't want to do. So the data set represents power plant readings, and it's things like relative humidity, and there's a number of settings at the power plant, and then there's the actual power output of this huge power plant. And it's real data from California, and it's some kind of electricity generation plant. And it's very important that they accurately guess what the output will be given the parameters they set at the start of the day, so that they can decide whether they need to buy additional energy, or maybe they're up for selling additional energy back to the market. And so there's this trading application piece. Unfortunately, the one with all the cool graphics is the wrong one I picked up. But if we just go through, so how you, if you hit the question mark in Karoo, it brings you a nice little menu up, which is super handy because I'm forgetful. And you can have a look and adjust all of the settings we looked at. So you can adjust all of those settings midway through a run. And we can go in here and we can hit a T to evaluate a single tree. So we're going to do an evaluation now on our best run. So we're going to list it. We saw 13 at the bottom. I understand from Kai that's the best one. And it's, T13. And now it's going to run through that data set. And it tells me we got a mean squared error of 10,000. Well, that's terrible, right? But this is only a few generations in. So now we're going to go and flip over to the one I had in the oven earlier. And we're going to look here. And actually, if I go back, here we go. This is the one I wanted to show you. I'm going to have to make the screen smaller. So in here, if I go into ID, it'll tell me the number of runs. So this isn't here. I'm on generations. So you saw 10 generations. This is 1,174 generations later. So this is like 1,000 years later for these guys, right? And look at the size of the equations we're getting. There's some really, really big equations in here. And I'm going to hit T27, and we're going to figure out what the regression is there. And we've got it down to a mean squared error of 24.5. Well, that's a lot better. So it does learn. So we really have got something that looks a bit competitive, 24.7. So now we're going to go back to our real experiment, because we've had our little kind of play there. So if we look at the experimental results then, was that interesting so far? Yep. Cool, okay. So we're going to go through the software about Karoo experimental results. So over the last month, I've been playing with this software and trying to get it better and better and better. And it turns out that there's a lot of tuning tricks. So I made the classic big data mistake of bigger is better. So I just went straight in without even knowing anything about GP. And I said, oh, you know, I'll have like a depth of 10 on my equations. I'll put in 1,000 individuals, and I'll run it for like 10,000 years. And I just fire off 7 of these on my GPU, and the office starts heating up, and they're all rubbish, right? I'm getting like a mean squared error of like 4,000. So I ring up Kai, or I write to him on the net. And I said, like, this sucks. And he's like, no, you're doing it wrong. So he then explains, no, what you need to do is choose your operators better. So he says you need to pick some ones that are going to be rich in terms of their complexity, and you need to add those coefficients. And if you look at here, you can see that these long numbers are the result of arithmetic operations in addition to sine and cos. And so it's come up with like constants, and it's folded those constants into numbers. So these are now adjusting the long equations, right? And you can see it looks kind of crazy, but that's an equation. I literally could write that on my arm, as I said, right? And so I got a best score of mean squared error of 23.5. Now, that was at generation 802, and you can see I'm up to like 11,000 because I'm trying to get better than that. And I have not been able to beat this. So I went in, and I'm going to show you the actual, because we're in demo mode. Everyone likes real stuff, right? So I'm going to go back in, and I'm running Zeppelin. Okay, so we're going to have a look at Zeppelin later. And I'm also running H2O. Do you guys know H2O? Pretty much everyone knows H2O. So here in H2O, we're going to import our files. So you can see I have the power plant data. I'm importing it. And I'm going to grab the one with features. Why not? I then can see the data that I've got there. I then run some stuff on it, and I don't really do much. I just split the data. So unfortunately, and it's been pointed out by Helen, who's a stickler, who looked at this, she said, oh, the split, you've got a different split. It's not apples and apples. And I'm like, I'm playing, right? So I split it again into the same ratios, 75% and 25%, but it could be a different random split. All right, sue me. So we're going to go and try that, and we're going to run some learning. So we're going to use cool data science. We're going to do XGBoost, because that's winning Kaggle. Everyone's all excited about that. So what do we think in the room? What do you think the mean squared error is going to be for XGBoost? Any takers for a guess? 13. Okay, 13. What algorithm in H2O will win out of all of them? Okay, so this data set, I can just show you, if I just say view data. Here's the data. Quite seriously, it is very tiny. There's 1, 2, 3, 4, 5, 6 variables of interest representing humidity. I think there's relative humidity, some settings for the station itself. There's the power output. This is the number we're guessing on the far right. So it's not really big. It's a very small data set. But when we look at the, actually, because we're not there anymore, I'm going to kill the connection on the VPN. And I'm going to see if I can't just go and have a look at that. Is that the one? Oh, man, there's the one with all the pictures. So it turns out this data set is noisier than I thought. So it doesn't have very clear relationships. But we'll continue on with the modeling. So I've then decided on that model to run a range of things. And I copied and pasted out of this notebook into my PowerPoint, into my thing here, the results. So let's just go through them. So the first one, 23.5, distributed random forest, standard settings, too lazy to change anything, 17. I think GP is like pretty competitive. That's not too far off, okay? It's not winning Kaggle. GLMs, I always kind of write them off. I'm like, GLMs, but they're useful. They're very useful. 17.1, still beating my genetic algorithms. XGBoost, 9.8. Man, it smashed it. Really, really good job. So what does that mean for us? Okay, so that was the end of the cool part. What did you guys think? Is that a great demo? Did you guys enjoy that? It's a real experiment. You guys can all play with this. I'll put all this stuff online. Okay, conclusions. Final thoughts. That's so annoying. Yes?
Did you count the time of execution?
Oh, okay. Yeah, so that's an important... So, well, let's talk about that in these conclusions, because actually that is exactly what I wanted to get to. So you're bang on. Okay, so final conclusions. If you're interested in this software or in this approach at all, I really recommend this software because it's just so simple to get started. And it's a fantastic tool to get started from scratch. And I want to thank Kai, if he actually watches this video, because he's done an amazing job with the software. He's folded in some very useful techniques, and he's super helpful. Okay, so that's a thank you. In terms of what would you do with the software next? So back in 1992, I ran my first neural network, and it had like 12 nodes. Oh, it was huge, right, on my 486. So fast forward today, and then you look at these gigantic models, in my view. All right, so what happens if we apply massive quantities of power to genetic programming? That's a question. I don't know the answer. I could be reaching. But what if we have massive gains, right? Because we never really tried this before, and no one's ever really done it before. So I think it's an open question for data science. Would we have massive gains? Because like some people really hit big with data science. Okay, so that's a question. That software we were running, when I got to the end of my run on the big complex one, it took longer to do the reproduction, crossover, mutation, and those abstract syntax tree manipulations than it did to run on the GPU. So the GPU was 6 minutes. Calculating the next generation was 9 minutes. So I was saying, well, hold on, this doesn't feel right. So I think that this whole endeavor is really, really ripe for mapping and reducing. Really simple idea. So I generate 100 random equations, or maybe 10,000 random equations, because I'm going to be scaling up. And I broadcast it to an RDD, and it sits on 1,000 machines, right? And then on each machine, I'm using Yahoo's like TensorFlow on Spark, and I kick off a local job that evaluates the fitness on my big chunk of data. So I got, I don't know, 15 terabytes of data spread out on these machines, and I do a chunk of that, and then I generate those fitness scores, and I collect and reduce them back to the home to figure out which are the most fit trees, and then I broadcast out a map to then rerun this. If we were to scale up using Spark, these techniques, I don't know if anyone's tried it. I haven't found it. I spoke to Kai about it. He thought it was really cool. There's a lot of opportunities. So I think your point about performance is bang on, because I'll be honest. I've been running that model full tilt in my shed for a month in the run-up to today to get a good result, to see if I can beat something, right? Because I had a mean squared error of about 60 for like 5 days, and I couldn't get it better. And then he gave me some tips on tuning around these point mutations and upping the frequency of them. So Kai's tuning helped me to get the number down to something that's competitive. I think that it could take a long time to do big runs. So I do think it needs to scale, right? What are your thoughts? Do you know?
Sorry?
Do you think that that's, what would you thought? Because
It's too slow.
you think it's too slow.
Because it's interesting actually to see how boosted trees would do. Probably would be less than a second.
So on H2O, it runs on my laptop. All of those models I run within like really responsive, like less than 30 seconds. Yeah, like not much at all. But it's a fairly small data set. So, yeah. Yeah. Tuning, it's hard.
So the first one, which I know is
Okay. To answer that question, I just realized I didn't flip back to my Zeppelin notebook and show you how I deployed it to the constrained environment, which was my promise at the front. So that equation that I generated with the MSE of 23, let's go and put it in a constrained environment and prove that we hit those problems. So let's just zip over to here, and let's just open that up. So, and then I'll try to answer your questions there. Can you guys read that? Let's make that, can I make that a bit bigger? Okay. So you can see this is a typical Zeppelin notebook. I've got a Spark reader. I'm going to read in the data set. So I've got my columns in there, really simple. It's going to flash in. I'm not going to run it here. I'll just zip up the page. Here is the equations. And I'm going to go back in and hit list to prove I can do this. Oh, did I just kill that? We'll connect that back up. Well, you can see I've already pasted that equation here. That's the 23.8 MSE that I got. That's the best one, 23.9. You can see I've been pasting them in. So I will run this for you now to show you this. So I've literally pasted in these equations. And if I go here and hit run, it's running, and it's finished, right? So we go and have a look, and this is just on my laptop. We've just generated the output of all those models in a SQL statement, and all of those different runs I have are there. And just because I'm going to be a cool kid, I'm going to take that data and I'm going to pop it into PySpark using cufflinks, and I'm going to put it into a data frame, and I'm going to recalculate over the whole thing the mean squared error of, so this is all of the data, including the test and train, which is unfortunate, but just to validate that I didn't make any mistakes. 25, which is about right, means a bit of overfitting there. And let's just visualize the data. So this is the time series data. If I run that again, just to demonstrate that I can do that. So these are the final model results. So it's a kind of a time series, because it's this data over time. Every time you see orange, it made a mistake. So that equation generated this time series. So it's in the ballpark, right? It's not terrible. So if you had to deploy this equation to something the size of a Tic Tac in a thing that sits on your wrist, actually this is okay, right? If this was a classifier deciding if you're walking or sleeping, it's probably good enough, right? But it can be deployed just with a copy and paste. So that was useful. Interpretability, you know, to be honest, is deep learning interpretable? You could use Lime, or we could use neurofuzzy techniques to get if-then-else, and maybe, but models aren't interpretable. So if I look at the error splits, so this is on the entire data set, because I don't know what the splits are from Karoo. That's an open ticket to fix it. You can see that actually I'm only plus or minus 10. Really, I could go to a user and say, yeah, you're like plus or minus 10, and it's normally distributed around 0 errors, right? So that's like a pretty good story to tell users. And I would have to explain to them the XGBoost is probably like really squishy, and it's looking like this, and you're going to lose some granularity on your model, right? But you're going to be able to get this thing into your legacy mainframe in DB2 on your Laravel RS6000, and we can do it in about 30 minutes with a stored procedure, right? That's an amazing story. So all these crazy requirements I'm getting, I can just say yes. So I'm really excited about saying yes, and even if I have to do it at slightly lower tolerances of quality, right? And maybe explainability didn't get better. So what do you guys think so far?
XGBoost is very easy to predict. I mean, the algorithm is extremely simple. And it will be pretty much, maybe a bit more complex than this formula, but it won't be really a killer for TikTok device. It will be like pretty much the same. It's just a tree.
It could be that we could port all of these models. So model portability is the question. But so I'm not saying that GP is the answer. I'm saying my investigations are to find out what's on the horizon. So I agree that if someone sorts out model portability more generally, then maybe it's not an issue. What I liked about this is that it's so simple, that bracketed equation with the scoping. I could literally paste it into Lua, and I know it'll run. It runs in Python just out of the box. I can put it probably in Clojure, it'll run, or Scala. I mean, I put it in Spark SQL. I mean, it literally is a small unit of code. And I think that what would be interesting is if I had to transmit this code somehow to 1 trillion edge devices to do some basic kind of smart thing, like, I don't know, like light bulbs detecting no one's in the room and dimming, something simple, that this would be compact and tiny enough that I could actually put it on this network. And people laugh, and I say, well, no, that's what the mosquito thing is all about in IoT, right? It's about minimum amounts of data being transferred. So I take your point. Big models can move around portably, but if we were in highly constrained environments, maybe.
I mean, not really big model. I mean, a boosting tree would be very tiny model. It would be like
Maybe, you know what, you could be right. I actually don't know how big those models are. Well, so it's a story of potential, a story of investigation. It was an experiment. It got you all in the room because it said TensorFlow, and I think Rich is going to be happy. All right, thanks very much, guys. Do you want to say some final words? All right, our man's going to say some words.
So thank you all for coming. Hope you enjoyed the talk. I think there is Subway here now, so there's food and there's drinks and stuff in the back.
And Andrew's around for a bit?
I'll be around for a half hour, an hour.
Andrew will be around to answer questions if you've got more questions. We've also got a little survey we'd like you guys to fill out, if you don't mind. Enter for a raffle to win some JetBrains tokens, keys. So, yeah. Well, thanks for all coming.
All right. Did you guys like? Did you like that?